뭐 처음에는 한국말로 할게요. 반갑습니다, 여러분을 만나서. 그 삼성 리서치에서 내가 오랫동안 그 자문을 하면서 지냈다가 3년 반 만에 오니까 그 아주 기분이 좀 새롭습니다. 그래서 오늘 여러분들하고 같이 얘기를 하려고 하는 거는 그 security라고 볼 수도 있고 아니면 safety라고 볼 수도 있는데 이게 그러니까 semi autonomous 시스템에 관한 걸 얘기를 하려고 그래요. I think from now on I'm going to speak in English. So 이게 안 나오네. 그래서 이 스크린이 안 나오는데 여기? Okay, I got it. 지금 오늘 그 포커스를 하려는 거는 그 세마이 오토노머스 시스템, 그 세마이 오토노머스 시스템이 뭔가, you have to think of something that can be controlled autonomously and also manually by human operator. This is a very common system we see and use almost every day. Actually, what we can see, for example, say autopilot, that started back in 1912. That's a long time ago. And ships, you have the autopilot that was started in 1920s. If you look at the automobile, I think everybody is familiar with self-driving cars. And there are there's 6 different levels of autonomy. The first one is no autonomy at all, no automation at all. And level 5 is fully autonomous, mind-free, feet-free, hand-free, all that. And all in between, you can see from your cars. I'm not going to spend a lot of time explaining this. I'm pretty sure you are familiar with this already anyway. And why do you want to have autonomous control? Well, it will be safer. For example, the number of accidents will be decreased by orders of magnitude. And also it will be eco-friendly. It will consume less fuel and emit less carbon dioxide. It is really good for the environment. And the third one will be more comfortable for the users. So there is a significant incentive why we want to have autonomous part. Well, then what's the state of the semi-autonomous systems? I'd like to point out that between this automated control and the manual control, if they are all consistent, then you don't have to worry about which one to use. You can use a manual control or automated control. But if they are different, which one should we use? Well, typically, I think we will trust humans more than the autonomous system. So you can provide priority to human or manual control over autonomous control. That is a fixed, like the static priority. Actually, this reminds me of one thing a long time ago. I was working on this automation of flight control system. And the NASA was trying to automate a lot of things. However, the pilot was always the king. If something pilot disagrees, a pilot can supersede or override or autonomous control because pilots can't go wrong. And I said, wait a minute, pilot can go wrong because they're tired or they can make mistakes. So if a pilot's input doesn't make any sense, airplane control system may reject pilot's sort of input. And instead, you are going to honor this automated control. And at that time, by the way, I'm talking about 20-some years ago, those people kicked him out, saying, pilot is the king. If you give a priority to something else over pilot, we are not going to do it. But now things are changing, though. I'm going to spend a little bit more time on that. Let me give you one example for automobile. I'm pretty sure your car is equipped with the adaptive cruise control and also ABS. If you look at the adaptive cruise control, you set your desired speed. And then your car will try to maintain the speed automatically. You don't have to press the gas pedal or apply brake. But if your car is too close to the car in front of you, you're going to apply brake. Then this ACC, adaptive cruise control, will be disabled automatically. In other words, the operator's input will have a priority over this automated control. On the other hand, if you look at ABS, if your car skids, whether you apply brake or steering wheel, the car will ignore your input. Because your ABS will detect the skidding of the car. How to detect this skidding of the car? You compare this engine RPM with the vehicle speed. Okay, engine is running very fast, but car is not running. Car is skidding. Once you detect that, this ABS will ignore driver's input. I'm pretty sure you know that, right? In the same car, you have two different philosophies. One is giving priority to human operator. The other one, you are giving priority to automated control. But we just accept them. That's what it is. And also, another one is always the input data to generate this control command or input are assumed to be trusted. However, this can be incorrect. Input data could be faulty or could be compromised, or even pilot's input or human operator's input could be malicious or could be faulty. What do you mean by malicious? I'm going to explain that in a minute. If that happens, this static assignment of priority to either automated or manual control is not going to work. Let me give you one example. I'm pretty sure you are familiar with this Boeing 737 MAX MCAS problem. MCAS is a maneuvering characteristic augmentation system. Essentially, what you have here the sensor at the nose of airplane, which measures sort of the angle of attack. If an airplane, this angle of attack is greater than 10 degrees, there is a possibility that airplane may stall. And therefore, you have to keep the airplane nose down. Otherwise, airplane is going to flip over. And you control this using this horizontal stabilizer, as you can see there. But if this MCAS sensor is faulty, in other words, it is not more than 10 degrees, but your sensor reading says more than 10 degrees, then this airplane will be a nose down. In other words, going down, not going up. Because that's going to happen, right? And if a pilot sees that, airplane is just a nose diving toward the ground, it's going to try to nose up using stick. And then the airplane is going to go up a little bit, but still the angle of attack sensor indicates more than 10 degrees. Then this MCAS will be activated automatically. So it's going to keep nose down. So there is sort of the competition between pilot and this MCAS. Pilot is going to nose up, and MCAS will nose down, up and nose. Actually, this controlling this horizontal stabilizer takes a lot of more energy. So if you fight over this for a while, pilot is going to be exhausted. And eventually, that led to two fatal crashes, killing about 600 some people. So all these 737 MAX were grounded for more than a year. And then there were a lot of investigations of why this happened, all this. So Boeing came up with a new solution. First of all, using two sensors instead of one. So if one sensor gives a wrong reading, you want to check whether the other sensor agrees with. And also they give a priority to the pilot. If pilot try to raise up, it's going to raise up, not just to nose down. So the FAA okayed, and therefore the airplanes are flying. However, what happens if a pilot is intentionally trying to make airplane nose down? Probably you know that German wing, the pilot intentionally sort of crashed the airplane. Whether the pilot was mentally unstable or something, that's what happened. Or the other is pilots are very tired. I'm pretty sure you read newspaper articles that pilots were tired, all this, and made mistakes. There are a number of instances like this. So this Boeing's new solution is not going to solve the problem. But nevertheless, I think these are now Boeing 737 MAX flights. I'm taking flights on those planes. I'm pretty sure you are too. And there are the other things that you can think of. But let me give you sort of these safety threats can be caused by plant. By plant, I mean physical system, either automobile or airplane. And the other one is controller. Controller is the computer hardware and software. So if you look at this plant side usually in response to whatever the control input it receives, and it will execute, but there could be faults in the design, or failures or attacks may occur during runtime, and therefore it's not silver bullet. And the one example you can think of, the Toyota's unintended acceleration. You know that took a long time. Actually, investigation took more than 3 years, and eventually I think they couldn't pinpoint what caused this unintended acceleration. Could it be hardware? Could it be software bug? Could it be driver's fault? And I remember a few years ago at Hotel Schiller, one driver drove into that revolving door and crashed it. Some of you may remember that too. And whether that was a driver's fault or a car's hardware fault, you don't know. In the end, I think they settled this out of court. On the other hand, this safety or security threat can be caused by controller. The controller could be human, could be automated control. Again, there could be design bugs or faults, or errors caused by fatigue or malicious intent. What makes things worse is there could be a lot of adversarial attacks. For example, you are familiar with this Jeep Cherokee hack 2015. These hackers got into the car through telematics system, eventually powertrain control system, and this Jeep was driven to the off-road. Nobody died. By the way, this happened during Usenet security, if I remember correctly. And also the researchers showed how to hack this GPS system for vehicle. Actually, the UC San Diego people also looked at this GPS hacking for airplane. That's quite possible. And the attackers can mount attacks directly to system operation, or it may mount attack indirectly going through system infrastructure. Or having said all of this, is there any way we can ensure this control of a semi-autonomous system, which is involved with both autonomous input and also human operated input, is safe in the presence of component failures or the human operators fatigue or malicious intent? In fact, this is a very, very critical problem. So I've been working on this for a long, long time, and finally I think we came up with some idea, and we started a new project about a year ago called CADCA, how to detect and resolve these control decision anomalies. And I'm going to spend most of the time for the rest of this talk on that. State of the art indicates either you have a trustworthy inputs. In other words, inputs are always trustworthy and they try to make other things reliable and trusted. But input data can be anomalous. Or you can have a usual the detection of sort of the anomaly. In other words, not following typical pattern. But this behavior inconsistency, not the same as a safety, I'd like to point out. And also sometimes you assume these measurements or observation is always perfect or complete and has all the necessary piece of information. But in reality, you may not be able to observe all necessary information. In other words, you have to achieve this safety in the case of limited data availability. For maybe cost reasons, you can't have infinitely many sensors to collect all the necessary information you want to achieve for safety. Somehow you have to achieve this safety and the security with limited data available to you. In other words, we have to sort of evaluate what sort of risks are involved when you have only a limited amount of data in the presence of sensor failures or malicious attacks. So this CADCA is more of the enhanced decision maker. Remember, decision maker could be autonomous entity or human, and I want to enhance the decision made by humans or these autonomous systems. So input here would be the control commands coming from, say, autonomous part or human, and also data coming from its own sensors, as well as data coming from elsewhere. If you're dealing with an automobile, the data may come from other cars or infrastructure, or even the people such as going by. They can provide the hand signals, or using smartphone, you can provide some data. What this CADCA does, when it gets the input, it will check whether this input is consistent, and therefore it can use to generate control signal or not. And once you find some inconsistency, I want to check what caused it, and how to restore consistent input. And then once you have that, and then you want to sort of assess risks involved with this reconstructed input data, and then whatever control decision you apply. And whichever, the least risk involved you will use. I'm going to give a little bit more details on that. So here you can see a very simple things, manual control, autonomous control, and the CAD curve would be a filter after these manual and autonomous control input, and then filtered or selected control input will be delivered to the actuator. And you turn motors and move your cars, airplanes, or if you're dealing with a medical device, it will control whatever this device is used for human, such as pumping in insulins or whatever. All right, there are three different challenges. First of all, once this I would call ego system, ego device receives the inputs. How does it know whether this received input correct or accurate? Second, if the input data is anomalous, can we infer what happened to the component which generated the input? And what I like to do is I like to reconstruct sort of a correct one from these anomalous data and also other data. And one thing that I like to point out that sort of the different states of a certain component may produce sort of the same data. If you're familiar with the control system, this happens, by the way. In other words, we want to reconstruct the state of that component, and we call it local view. And once you have these reconstructed local views, all this, can we sort of evaluate what risks are involved with whatever decisions are available for you to use? Essentially, what we like to point out that the control decisions will be dependent on the operation context. For example, if you drive in San Francisco, when you drive up, even if you press gas pedal very hard, the car is not going to move very fast. On the other hand, if you go downhill, even if you don't apply gas pedal, the car will go very fast. In other words, this slope is a context, operation context. And the curvature is the same thing. If you have sharp turns, you have to do differently. And also, if a road is icy or there is a traffic jam, there are all different contexts. So you have to consider this context. How do you know this context? Well, human case, you see with your own eyes or hear with your ears. But in this the computer system, you have to evaluate or estimate operation context. And then there's the risks involved would be consistent with its operation context. All right, let's look at this ego entity. That's a car, say semi-autonomous vehicle. This is a typical sort of a cyber-physical system. You can think of it like this. You have a CAD car using manual and autonomous control as an input, and you are going to determine which one to use. Actually, you can generate a new one too. You don't have to use either, but you can generate new one. I'm not going to talk about that much. And then that control decision will be delivered to the actuators. motor is going to turn, and then your physical system will change its state, and then it will be detected by sensors like a position, velocity, acceleration, or torques, or whatever have you. And also the other data will come from other entities, other cars and the like, and then come back to this autonomous and the manual control as input. And then things can go wrong here for autonomous control part, or malicious human operator, or these actuators or sensors could be compromised. Sensor cases, spoofing attacks, or adversarial sort of the attacks you can think of, or the inputs coming from other entities, say other cars, or roadside units, or even base stations, if you like, because you're working on edge computing. That's what you may say. One thing that I'd like to assume, though, our CAD implementation itself is trusted. If you cannot trust that, all bets are off. Now, how to make that trusted? There are a number of ways you can do. You can have diversity, you can have redundancy, or other stuff. But I'm not going to cover that. Well, I like to look at these three different levels of a threat, depending on the attack attributes. Say, number of data types under attack, say positions are compromised, velocity compromised, or the heading is compromised. So depending on the number of data types are under attack, will be harder or easier. Or do these attackers know the correlation between this data? Because this correlation between data is an important part. You can view this as a physical invariant. I'll just give you a little bit more detailed examples later. And also number of different entities, components on the attack. And also you may say, is the ego vehicle under attack or not? So because you have to consider the possibility that your ego vehicle is on attack. So the simplest case is a naive attack, a naive threat. The attacker doesn't know this data correlation or whether this data really indicates sort of normal behavior. It does not have any idea at all. So essentially, you have a simple sort of a blinded attack, compromising data or whatever. Whether it's compromising multiple data or single data, you have a different scenario. So in that case, by the way, you can have a single data or multiple data without any knowledge of a correlation of the data. That's the first level. The medium level is this single entity attack, but it has a knowledge of a correlation of data. In other words, it has a knowledge of some physical invariance of the system. And if, say, normal data correlation is a matching, since the attacker knows that information, whether it will see whether this ego vehicle is compromised or ego vehicle is normal or not, it is a bit more sophisticated attack, but it is not the most serious attack. The third one is we call the sophisticated attack. Multiple entities are under attack with the knowledge of data correlation, and therefore attacker can match this data correlation, and therefore detection mechanism or defense mechanism may not be able to infer what is going on. Compared to this medium level, this attacker can compromise multiple different entities. So Kafka cannot handle all possibilities. Easier ones, such as naive attack, we can detect anomalies and we can guarantee safety. That's pretty good. And also the even medium level, we can provide both the guarantees on detecting anomalies and ensuring safety. But if you deal with the sophisticated threat, you can detect anomalies, but you cannot ensure safety. Okay, before I present details of the Kafka design, let's look at the important concept, which is consistent with the law of physics. And we define the notion of detection set or verification set. Suppose we have, say, data types x1, x2, blah, blah. As I said, this could be position, velocity, acceleration, heading, whatever have you. What we do is we divide these data types into multiple overlapping subsets, each of which is called detection set or verification set. So here, x1, x2, x3, x4, x5 is one group, and the x6, x7, x8 is another group. But remember, the second one and the third one, they have an overlap, x8. And then from this, you come up with, say, the inconsistent detection function. Essentially, what we do is the group of variables are correlated, and therefore you can estimate, you can predict. For example, if you do the position and velocity and acceleration, if you have a position data at time t1 and t2, x of t1, x of t2, and you can estimate velocity between these two positions, right? t2 minus xt1 divided by t2 minus t1, that would be average velocity. And you have a velocity sensor as well. So if this estimated velocity is very similar to measured velocity, then we'll say we'll trust. If they are very different, you may, there's something wrong. And the other things that we worked on, for example, you have a smartphone and a car. There are a lot of sensors overlapping. Smartphone has a position, velocity, acceleration, IMU sensor, all that. Vehicles have them too. So if you measure these data from vehicle sensors and smartphone sensors, you can correlate them to check whether there is any malfunctioning or compromised sensor data. That's the idea. Of course, if you deal with the phone sensors and vehicle sensors, quite different, because phone sensors, depending on what you do, if you do this, IMU sensor reading will be very different. So you have to filter them out. So there are some challenges. Nevertheless, you could do that. And why this is important? These vehicles don't come with a lot of redundant sensors for cost reasons. And the people carry smartphones anyway. So there is a free redundant sensor readings already. So why don't we just make use of them? That's the idea. So using this estimation prediction, also the define and extract features, you may be able to detect anomalies. So this Kafka consists of three important sequential components. First, once you receive data, you want to see whether this data is consistent or not. So consistency check. And once you detect inconsistency, you want to construct local view that I mentioned earlier. Once you have a local view, then what control you want to apply, and each control will be assessed for its own risk. And then you choose whichever has the least sort of a risk. These are the examples I mentioned. You can use a position, velocity, acceleration, heading, and the yaw rate, all that. And you use a P and V as one, say, detection set. V and A as another detection set. Heading and the angular velocity is another set. And then by comparing, you can detect sort of the inconsistency of data. Once you detect this inconsistency, essentially you are going to have a sort of Boolean equation. So this consistency check will produce sort of equations for equation system. And solving these Boolean equations, that's sort of the fitting set problem. So it's NP complete, as you know. So you have to use the heuristics. And then when you detect this inconsistency, whether this inconsistency caused by operation context, as I said, you go uphill in San Francisco, even if you press your gas pedal, car is not going really fast. Does that mean your gas pedal, this position sensor is malicious or faulty? Probably not. The braking is the same thing. So essentially by doing this, you will eliminate these false detections. I mentioned these heuristics. I'm not going to go over all of this. I'm going back to this the threat model. Essentially, this algorithm that I just presented in the previous slide will cover this the threat model that I mentioned. Greedy algorithm. Actually, I have the 6 different algorithms. Essentially, the greedy algorithm or this solution space algorithm will provide this search space for different sort of possibilities, and then different possibilities will sort of define the solution or find the solution. And then finally, we can reconstruct this local view by solving this. All right, for this last step of this processing pipeline, risk assessment, we want to determine this unsafe control decision. Local view, say greedy algorithm, you have the 5, 6 different algorithms. And then the control input could be a 1, 2, 3, whatever. Local view plus control decision. Then I think we can assess the risks involved. And what other metrics to use this risk assessment? If you worked on, say, autonomous car, there are a lot of papers dealing with the risk assessments. For example, your vehicle is very close to, say, off-road, or very close to obstacle. They measure this risk based on, say, distance between this ego vehicle and the obstacle, or distance between this ego vehicle and the boundary of the road. This is somewhat similar. So our case, we say apply this control. Then we want to evaluate, say, time to moving to unsafe state. how much time do we have before this vehicle becomes unsafe or unsafe? Or the other is time to collision. How much time will it be there before this ego vehicle collide with the obstacle or another car? Usually the time to unsafe state is smaller than this time to avoid the collision. This can be viewed as a safety concern. If you find that your solution say the system will never go to unsafe state, whether it is a human control input or autonomous control input, doesn't matter. You will choose it because it's safe. But if that's not the case, in other words, the system can go this unsafe state, then which one to choose? Obviously, you want to choose this least unsafe sort of a control decision. But this also has some issues. All the things that we get, or the sensor data, you look at history of this data. This subsystem provided certain measurements in the past, which was not really unreliable. It's almost like a reputation system. So you have to look at this. And of course, you have to look at the timing aspect. In other words, the unreliable input provided 1 hour ago shouldn't be accounted for more than the input you got 5 minutes ago. Okay, so you have to have forgetting factors involved. We have a case studies. I have only 3 minutes left. The ego vehicle on the top, and there are 2 other the neighboring cars. And then the external measurements, by the way, your own car will be able to determine its own location, and also it can measure the cars in the neighborhood. And also the other cars may broadcast its own position, velocity, acceleration, heading. This is a sort of BSM, basic safety message sort of protocol. This PSM stuff, I have to say that one time I think the US tried to mandate all new cars will be equipped with these capabilities. So all the cars will broadcast basic information to all other cars. And then that mandate thing was never enforced, by the way. So this information may not be available. This is a scenario. And then we apply all these consistent checks, local view construction, and the risk assessment, and then calculate this time to collision, or what's the minimum time required for your autonomous control or drivers to handle this. We use the human's reaction sort of the pattern. And this is very similar to this robot path planning. Actually, the autonomous vehicle, you have to have path planning, just like a robot. You can do this path prediction. This is a very simple thing. It's not only for autonomous cars. There are many other things that work out this way. All defense systems, like detecting enemy missiles and the launching sort of the anti-missile, like detecting drone attacks, you launch your missile to shoot down. It's the same thing. Actually, my time is up, so I'm gonna I'll skip all of this. I'd like to go to a final. Oops. This Kafka is more of the concept of securing semi-autonomous system. As I said, the semi-autonomous systems are sort of everywhere. Your home or cars, robots, drones, ships. And essentially, this is involved with general system structure or concept, three-stage pipe. And you have to have a domain-specific design, just like an AI system. This machine learning is not going to give you a perfect answer for your system automatically. You have to have your domain knowledge and utilizing this machine learning technique. Essentially, I think you have to deal with the safeties. And there are a lot of things ahead of us to do to secure these semi-autonomous systems. I think slides will be available to the audience, and hope if you have time, you can go through slides that I didn't cover. So whatever questions you might have, I'll be happy to answer.
네, 일단 교수님 발표 준비해 주신 거 너무 잘 들었습니다. 저희들이 이제 질문을 좀 받아보도록 할 텐데요. 질문이 있으신 분들은 손을 들어주시면 저희가 마이크를 가져다 드릴 예정이고요. 질문은 한국어, 영어 둘 다 편하신 대로 하시면 저희들이 통역 서비스를 제공해 드리고 있습니다.
You can ask questions in Korean too.
네, 저희 맨 앞에 마이크 좀 받으리.
예, 삼성 리서치 아메리카의 장영진입니다. 오늘 교수님 발표 되게 잘 들었습니다. 그 센서 인풋을 하나도 신뢰하지 않는 상황에서 시나리오별로 디시전 메이킹을 하는 것이 되게 인상이 깊었는데요. 제가 소프트웨어 연구를 하면서 반대로 교수님께서 발표하신 그 센서 인풋을 하나도 트러스트하지 않는 상황에서 그 디시전 메이킹을 하는 게 되게 인상적입니다. 근데 여기서 그 피지컬 인베리언트를 말씀하셨잖아요.
네.
근데 제가 이제 리얼타임 시스템은 아니지만 다른 시스템에서 보기에 이제 패킷을 한국에서 미국에 보낼 때도 빛의 속도보다 빨리 갈 수 없다라던가 시간의 방향은 앞으로만 흐른다 뭐 이런 게 들어가는 가정이 많은데요. 여기서 센서를 안 믿는다라는 가정이 되게 훌륭한 가정인데 그 이전 연구들과는 좀 차별을 두지만 예를 들어서 단 하나의 센서만 트러스트할 수 있다. 뭐 이렇게 되면은 아마 그 멀티 엔티티와 그 컨스트레인트를 맞추는 그런 공격에 대해서도 아마 세이프티를 보장할 수 있는 솔루션이 있을 수도 있다는 생각이 좀 드는데요. 그 트러스트 월티한 센서를 딱 하나 정도 이렇게 가져갈 수 있는 가정을 그 리얼타임 시스템에서 할 수 있는 건지 여쭤보고 싶습니다.
That's a good question. Actually, this invariant thing is very important. It's a mother nature. In IT, though, it's not just a law of physics, but there could be a lot of the man-made sort of references. Just like this is not the semi-autonomous system. For example, if you use a credit card, typically you use less than, say, $500. Suddenly, your credit card company detects you used, say, $5,000. They'll text you or send you, is that you? Or you use a credit card in Seoul only, and suddenly use the credit card in Tokyo. Is that you? So what is that? Essentially, I think the system develops sort of the reference pattern. And if it deviates, before rejects this credit card charge, want to make sure whether it's you or not, right? And of course, the question is how to establish this reference. That's a very important part. Sometimes this reference you established doesn't stay fixed all the time. you spend all the times less than $500, but suddenly I think you decide to use $5,000. But still it's you, and the credit card case you can check. But cyber physical system case you don't. You have to do execute or not on the fly. So it's a much harder problem. Well, how to deal with that? Essentially, you have to establish this and test as much as possible, just like FAA. FAA is kind of the collection of statistics on all these anomalies and accidents, and put in the testing scenario. So if you build a new airplane or a flight control system, that will be tested against all these collected sort of behavior patterns. And nothing went wrong for, say, more than 10 or 12,000 hours. FAA will certify you can fly. And then you may say, what happens if this anomalous behavior was not in the testing scenario? Well, it's bad luck. Accident will occur, but that case will be added to the testing scenario. So this FAA testing scenario is an accumulation of all these statistics over a long period of time. But I think a 1 in million or 1 in billion, that testing scenario may contain real one. That could happen. So it is very, frightening. I would say, am I flying airplane which is not formally specified and proven to be safe? Yes, we are. Yes, we are. Actually, there are many other things that work out that way, though. So I think by the way, this concept is not new. If you look at the control part, always you generate reference trajectory and compare the actual trajectory against a reference trajectory and measure the deviation. Robot path planning is the same thing. You measure the deviation from this desired trajectory. If it deviates too much, it's going to collide with something. And an airplane autopilot mode is the same thing. So I think this is a pretty interesting problem. Anyway, I think I digressed a little bit from what you asked, but I think that's a very good possibility.
네, 그럼 시간 관계상 질문 1개 정도만 더 받을 수 있을 것 같은데요.
So I think the framework looks very challenging in terms of evaluation perspectives. So my question is about what are your plans for collecting the data and how you plan to use the data to actually evaluate the framework?
You mean how extensive a data set should it be or expensive a data set?
Yeah, so the framework looks very challenging in terms of evaluating the system.
Uh-huh.
So my question is, how do you plan to collect the data and try to evaluate it? Because data collection looks really challenging right now.
Okay. I think that is a more heuristic way we do. By the way, you have a data set. I said that we divide this data set into overlapping subsets and call the verification group or detection set. And how you do that, depending on what you are looking for, especially the example I gave you is based on law of physics. Just like the position, velocity, acceleration, they are related, or heading and angular velocity, but they don't have to be correlated through this law of physics. You can artificially sort of build a sort of a relationship between the two. Just as I said, about credit card case, your spending pattern, that's not law of physics, but based on statistics. You spend money in Seoul most of the time, and you spend less than $500 for each transaction. That's not law of physics, but more as a sort of the statistics that you built over the years. But this can change as a function of time. Now that you're making more money than, say, 10 years ago, so you may spend up more than $500 per transaction compared to 10 years ago. So you have to change this as the time goes on. So this data set, I'm not quite sure.
네, 아무래도 저희가 흥미로운 주제이기도 하고 답이 딱 나와 있는 주제가 아니다 보니까 여러 질문들이 많으실 것 같은데요. 저희가 시간 관계에서 아쉽지만 질문을 여기까지 받도록 하겠습니다. 신광 교수님께서 나머지 시간 동안 이제 계실 수 있을 텐데 그때 따로 또 여쭤봐 주시면 감사하겠습니다. 수고해 주신 우리 교수님께 다시 한번 큰 박수 부탁드리도록
네,
하겠습니다.
감사합니다.